Good day everyone, my name is Darren Jade Marasigan from Group 3 and we are assigned to report building water supply system. So let's begin. Main parts of a water supply system. Plumbing codes require that a potable water supply be adequately furnished to all plumbing fixtures. The water supply system in a building carries cold and hot water through distribution pipes and delivers it to the plumbing fixtures. The water service line carries water from a district supply pipe to the building. The main parts of a typical water supply system include the following. But before that, let's familiarize ourselves first with examples of rigid pipe distribution configuration. The first one is the residential type. Just look at the illustration for more information. The next one is a commercial rigid pipe distribution configuration. Dumako na tayo sa main parts of water supply system. The first one is building supply. The building supply or water service is a large water supply pipe that carries potable water from a district or city water system or other water source to the building. Please remember the specification here, potable water. Next is water meter. A water meter is required by most district water supply system to measure and record the amount of water used. It may be placed in a meter box located in the ground near the street or inside a building. Next one is the building main. The building main is a large pipe that serves as the principal artery of the water supply system. It carries water through the building to the farthest riser. The building main is typically run or located in a basement, in a ceiling, in a crawl space, or below the concrete floor slab. Next one is riser. A riser is a water supply pipe that extends vertically in the building at least one story and carries water to fixture branches. It is typically connected to the building main and runs vertically in the walls or pipe chases. Next one is fixture branch. Fixture branch is water supply pipe that runs from the riser or main to the fixture being connected. In a water supply system, it is any part of a piping system other than a riser or main pipe. Fixture branch pipes supply the individual plumbing fixtures. A fixture branch is usually run in the floor or in the wall behind the fixtures. Next is fixture connection. Fixture connection runs from the fixture branch to the fixture, the terminal point of use in plumbing system. In a fixture connection, terminal points are accompanied by various devices. Example, a shut-off valve. Shut-off valve is typically located in the hot and cold water supply at the fixture connection. Let's move on to the general water distribution system layout. The water service pipe is an underground pipe that is typically called a lateral. It extends from the underground street main that is part of a district or city water system and delivers pressurized potable water to a building plumbing system. The water service lateral is connected to a water meter that measures consumption. The water meter is typically located in an underground car box located in the building's front yard or is located in the building interior, in which case it is connected to a remote readout on the exterior of the building, which allows easy access for meter readings. If the building plumbing system is served by a well, a water meter is not needed unless monitoring of consumption is required. A water service shut-off valve is typically located at the meter location. As the building supply piping enters the building, pipes split off to supply water to hose bibs, the irrigation system, and any industrial process equipment using water that does not need to be heated. Like what I said a while ago, a building shut-off valve is typically located at this location. If pressure available from water service is too high, a pressure-reducing valve or pressure-reducing arrangement drops the water pressure to an acceptable level. If water softening or treatment is desired in the building, water is passed through a softening or treatment device before the water is distributed to the building. Water softening or treatment is done after irrigation water and or water process equipment is removed. Once the water supply main passes through the softening or treatment device, if it is used, the main pipe splits to provide water to a water heater or water heating system that generates hot water before it is distributed. Next one is a fixture connection links the hot or cold water branch to the fixture, the terminal point of use in a plumbing system. A shut-off valve is typically located in the hot and cold water supply at the fixture connection, like what I said a while ago. Air chambers are installed as close as possible to the fixture valves or faucet and at the end of long runs of pipe to reduce water hammer. In a conventional rigid pipe water distribution method, fixture branches extend from a riser or main to the individual fixture being connected. A fixture branch is usually run in the floor or in the wall behind the fixtures. In the innovative home run water distribution method, individual branches begin at a main manifold located in a utility room or basement, usually near the water service. Individual hot and cold water branches extend uninterrupted to each plumbing fixture or fixture group. The distribution configuration methods are described in the following. Here it is. In the conventional rigid pipe distribution configuration, the hot and cold water distribution pipes are installed parallel to one another as they convey hot and cold water to risers and branch pipes. Running pipes parallel with building walls and floor arrange pipes in an organized manner. Hot and cold pipes should be spaced at least 6 inches or 150 millimeter apart or have insulation placed between them to prevent heat interchange. Got it? In top quality work, both pipes should be insulated so that hot water pipes minimize heat loss and cold water pipes prevent surface condensation. A branch supplying water to two or more fixtures is called a zone. A zone can supply one or many fixtures on one group or on a few floors. Fixtures are typically located in cluster cold groups. For example, in a commercial building or school, restrooms for men and women are grouped together with fixtures arranged against a common plumbing trace. That is, fixtures back up on both sides of walls enclosing the plumbing trace. Water fountains are also located in the area of the restrooms. Likewise, a set of shower head is located on a common trace or wall. A group arrangement allows several fixtures to be served by the same water main or branch. For efficiency and convenience, risers and traces should be located near plumbing groups. In wood and light gauge, steel frame construction holes are drilled or cut to allow the passage of the pipes. Holes are located in the center of the framing members to avoid nails or screws penetrating the pipe and to minimize structural damage in load-bearing members. Metal plates cover pipes in wood framing when the pipe surface comes too close to the surface of the framing and there is a possibility of nail or screw penetration. There are times when the width of a wall need to be increased to allow for pipes running horizontally to pass by drainage pipes or other pipes running vertically. Walls of increased thickness are called plumbing walls. The spaces in the open web of wood or steel truss construction, we have an example here, I forgot to write this. Wood trusses and steel joists make it easier to run piping through these structural members without affecting their structural integrity. It is sometimes difficult to feed long lengths of pipe through closely spaced trusses or open web joists after they are installed. Difficulty also exists where pipe encounters some other large pipe or ductwork going in the opposite direction. That's why coordination is necessary with the subcontractors erecting the trusses and installing the heating, air conditioning, or ventilating ductwork. On projects with concrete walls and ceilings, it is typically necessary to provide slits or holes in the concrete for the pipes to pass through to get from space to space. It will also be necessary to provide inserts and hangers to support the pipes. Pipes placed below poured concrete slabs and in concrete, steel composite decking must be placed before the concrete is poured. Typically, both the water supply and drainage pipes are laid out next to each other because they go to the same areas of the project. Many times there are plans so they will come up in a partition. So remember this, accurate placement of piping is very crucial. Tub, shower, and water closet piping will need to be placed in the exact location where the fixture is to go. All piping must be carefully located and the system checked for leaks for the concrete is poured because any relocation or repairs of pipe would be costly. And as engineers, we must avoid such thing. Let's always take note of the word economical. In multi-story buildings, risers and pipes that carry water vertically through walls or through enclosures called chases. A chase is a vertical opening through a floor or several floors that is enclosed with walls between floors. A chase can enclose piping only, or it can enclose electrical wiring and or mechanical system ducting and or pipes that run vertically from floor to floor through the building. This one is informational, so it doesn't make sense anymore to elaborate this. Pipe tunnels may be used on large projects to provide concealed space for the passage of mechanicals at ground level and from building to building. Hangers from the top or side of the tunnel are used to support the pipes. That's it. So access may be from either end of the tunnel or access floors may be provided. Ready accessible valves used to close off the water supply to a fixture, appliance, or system are called shut-off valves. To define shut-off valve, a shut-off valve is required on the discharge side of the water meter. When more than one building is severed by a single water service line, a shut-off valve must be installed at each building. A readily accessible shut-off valve must be installed on the cold water supply line feeding a water heater in the proximity of the appliance. In multifamily installations, single or multiple shut-off valves must be installed in each dwelling unit so water to the unit can be shut off without interrupting the supply to the other units. Valves must be accessible in the dwelling unit they control. Let's move on to the home run manifold distribution configuration. A home run or manifold distribution configuration consists of a plastic or metal plumbing manifold and flexible plastic piping. The manifold serves as a common location from which all the plumbing fixtures are supplied. Manifolds have two separate chambers, the cold water chamber and the hot water chamber. The cold water chamber is supplied from the main water supply line, while the hot water chamber is fed from the water heater. A water line dedicated to each fixture originates at a port in the manifold and extends to the individual fixture, so fewer fittings are required. Some manifolds offer shut-off valves so each fixture can be turned off individually at the manifold. In a hybrid configuration, termination or secondary manifolds may feed the plumbing requirements for a room or set of rooms and reduce the number of fittings required in the plumbing system. Home run configurations typically use cross-linked polyethylene or what we call PEX or composite PEX-PEX piping, which is suitable for cold and hot water use. Because of the flexibility of PEX, there is less of a need for piping teeth and elbows. With one fitting needed at the manifold and a second transition fitting at the fixture, a single run is made from the manifold to the fixture. As a result, home run configurations can be installed more quickly than rigid plumbing. Fittings and coupling are available for unique situations such as creating changes in direction that are tighter than the minimum bend radius allowable for the piping. The home run configuration requires much more pipe than the rigid configuration, but the plastic pipe used is much less expensive than the metal or copper pipe used in the rigid pipe configuration. As a result, the home run configuration is typically cheaper. Home run configurations equalize pressure which allows several fixtures to be operated simultaneously without drastic changes in pressure or temperature. Because each fixture has its own supply line, the size of the pipe can be adjusted for a fixture's specific use. In addition, for some fixtures, PEX piping can be downsized, usually 1/8 in diameter smaller, in comparison to a conventional rigid piping configuration. Another trivia is that a smaller diameter means that hot water arrives at fixture faster, and less hot water is left standing in pipes after a fixture is operated. Variations of this distribution system are described in the paragraphs that follow, but before that, let's take a look at these pictures. The first one is the manifold of a home run water supply distribution configuration. Sabi dito, water enters the manifold at the bottom. The pipes at the top of the manifold serve and return from the water heater. flexible pipes or cold water on the right and the hot water on the left run to individual fixtures. The second one is a clearly marked set of hot water left and cold water right ports on a manifold. Yung nasa left po, mga mark yun sa hot water, yung nasa right, sa cold water po yun. Marami pa po siya actually na mga pictures. Pwede nyo naman po i-post yung video tapos take a closer look para mas lalo pa po nating maintindihan. The backside of the terminating fitting at the end of runs of PEX pipe in the home run water supply distribution configuration. Dito po tayo sa up feed and down feed distribution. We have here two basic types of water supply distribution system. They are used in buildings. The first one is the up feed or upflow system. The second one is the down feed or downflow systems. Dito na po yung yung mga variation na darating. May mga paragraph po ditong susunod. Up feed and down feed distribution. Okay. In a conventional up feed system, water pressure from the water supply main is relied on the drive water flow through the system. Water pressure in building water supply mains typically ranges from 40 to 80 psi or 275 to 550 kilopascals with 80 psi or 550 kilopascals considered the upper limit for most systems plumbed with metal pipe and 40 psi the upper limit for plastic pipe. Take note po na yung PSI is an abbreviation for pound force per square inches. This available pressure places limits on how far water can be driven upward in a plumbing system. Part of the available pressure is expended in friction losses as the water passes through the meter and the various pipes and fittings, and part of the pressure is expended to overcome gravity, which is the pressure required to push the weight of water upward vertically. Up to the riser. Vertically up to the riser. Additionally, there must be sufficient pressure left at the remote fixture to drive flow of water through the fixture. It takes 0.433 psi to push water up to 1 feet vertically, or in the SI metric system, 9.8 kilopascal to push water up to 1 meter vertically. Conversely, a 1.0 psi pressure can push water upward 2.31 feet vertically, or in the SI metric system, 1 kilopascal to push water up to 0.144 meter vertically. This concept is further discussed later in this chapter by my other groupmates. So yun nga. Pushing water of 20 feet, 6.1 meter vertically requires a pressure at the base of the riser of at least 8.68 psi or 42 kilopascals, because 20 times 0.433 psi is 8.68 psi. Wait po, 3 times 2 is, this should be 8.66. Oo, 8.66 to. Sige, baka baguhin na lang po natin dun sa handout na ipro-provide. So, next slide na po tayo. If a pressure of 80 psi or 550 kilopascals is available at the base of a plumbing system riser, the maximum height water can rise vertically is 185 feet or 56.5 meter, because 80 psi times 231 feet is 185 feet. Sige, check ulit natin, baka mali po. 80 times 2.3 is 1 times 8. 8, 3 times 8, 24, 2 times 8, 16. It should be around 184 something. Got it. 184.8. Yep, correct. By rounding up, we got 185 feet. Depending on the exact floor-to-floor height, a pressure of 80 psi, 550 kilopascals, would drive water about 15 stories, but only if there were no friction losses or fixture operation pressures to consider. When When friction loss and fixture operation are taken into account, practical design limitations typically establish about 60 feet or 18 meter as the standard maximum height of 40 feet or 12 meter as the preferred maximum height. This limits a conventional upfeed system to buildings with a height of about 5 stories. Mga specification na po ito eh. In tall buildings, water must be supplied through a pumped upfeed distribution system. A pumped upfeed system is one in which water entering the building flows through pumps that maintains adequate water pressure throughout the structure sufficient to operate any plumbing fixture. In a high building, example 50 stories, water enters one or more pumps where its pressure is boosted to pressures of 150 to 250 PSI. Okay. PSI po yan na. Tapos pag kinonvert po natin siya sa kilopascals, it will become 1,000 to 1,700 kilopascals or more. A vertical riser carries this high pressure water to fixtures at the top of the building. Such a pressure in the distribution system is too great to use plumbing fixtures. Example, lavatories and water closets. The pressure reducing stations, which are located about every 10 floors, monitor and adjust for any variation in pressure. This ensures that water available to plumbing fixtures is always kept under a constant pressure. For this reason, at several zones, water is removed from the vertical riser, reduced in pressure at pressure, reducing stations, and distributed to the fixtures in that zone. In buildings that cannot be adequately serviced to the top floor by an upfeed system, water is pumped to elevated storage tanks in or on the building, and the water is fed down into the building by gravity. This gravity system fed from the upper stories to the lower. It is called downfeed distribution system. Water entering the building flows through pumps that develop sufficient water pressure to drive water to storage tanks serving zones of about 10 floors each. To develop adequate pressure, the storage tanks are placed above the zones that they serve. Ito po yung mga figures para mas lalo po nating maintindihan. Take a look closer na lang po sa pics. Pwede po nyong i-post itong video, and that's it for upfeed and downfeed distribution. For continuation, let's now talk about water pressure considerations. Hydrostatic pressure. A fluid, it's either on a gas or liquid state, molecules tend to seek equilibrium or in a stability of forces. When forces acting on a fluid are unequal, molecules in the fluid move in the direction of the resultant forces. Therefore, an elementary property of any fluid at rest or not flowing is that the force exerted on any molecule within the fluid is the same in all directions. A hydrostatic force is a force exerted by the weight of the fluid against the walls of a vessel containing the fluid. And hydrostatic pressure, the hydrostatic force per unit area is perpendicular to the interior walls at every point. If the pressure were not perpendicular, an unbalanced force component would exist and the fluid would flow. If gravity is the only force acting on a fluid, example, the water in a gravity plumbing system, the hydrostatic pressure at any point in the system is directly proportional to the weight of a vertical column of that water. Additionally, the pressure is directly proportional to the depth below the surface and is independent of the size or shape of the container. In Tagalog po, ang tinutukoy na hydrostatic pressure dito ay yung puwersa na ibinibigay ng kalmadong tubig sa isang saradong lalagyan or container po. For example, you have a glass of water. Yung force na ina-apply ng water sa glass is the hydrostatic pressure. Hydro means tubig, static means di gumagalaw, and pressure means puwersa. That's it. Water pressure. Water pressure difference is the driving force behind fluid flow. Water pressure available at the water service is lost as water flows through the piping of a plumbing system. This pressure loss or pressure drop in a plumbing system is from friction loss as the water moves through the system and pressure loss as water is forced to a higher elevation. Kung ang hydrostatic pressure is pertaining to the force of water at rest, ang water pressure naman ay tumutukoy sa driving force ng moving or flowing water. Pressure is high kapag galing sa mataas na lugar, pababa, ang flow ng water. And the pressure is low when it's the opposite. Water pressure available at the water service is considered acceptable in the range of 40 to 80 psi or 275 to 550 kilopascals or greater in mountainous regions. In most residential and commercial system, the upper limit is 80 psi or 550 kilopascals. Some systems with thermoplastic supply piping set the upper pressure limit much lower, usually about 40 psi or 275 kilopascals. When water service pressure is deemed too great, a pressure reducer is used to limit pressure and reduce potential for leaks in the thermoplastic supply piping. Dapat po kasi nating iwasan yung mga leaks. Kaya ginagawa po yun. An insufficient pressure at a plumbing fixture results in low flow of water at the fixture. An excessive pressure at a fixture may cause disturbingly high flow, will waste water, and may cause damage to our premature deterioration of the fixture. So it means ay dapat sakto lang ang flow ng water natin to avoid low flow of water or excessive flow naman na nagkakos ng pag-aaksaya sa tubig or pagkasira ng ating mga fixture. Residual water pressure is the pressure available at the outlet just before a fixture. It affects water output of a fixture. Nakakaapekto po siya sa water output ng ating fixture. The residual pressure requirement at the many types of plumbing fixtures varies. Code specifies that the highest or most remote outlet fixture have a minimum pressure of 8 psi or 55 kilopascals for flush tanks and 15 psi or 103 kilopascals for fixtures with a flushometer valves. Here is the required residual pressure na nakascale po sa dalawang unit. First is PSI at yung sa kabila naman po is kilopascals. Tingnan na lang po natin itong image para mas lalo po nating maintindihan. Pressure difference. When forces acting on a fluid are unequal, molecules in the fluid move in the direction of the least pressure. Fluid flow is caused by a pressure difference in the fluid. A pressure difference must exist at a plumbing fixture to cause water to flow. That is, water pressure at the fixture must be at a higher level than atmospheric pressure for water to flow from the fixture. Pressure difference or delta P is the driving force of fluid flow. A fluid will always flow from a higher pressure region to a lower pressure region. Tandaan po natin yan. Nature yan ng tubig, kaya wala tayong magagawa. So, our choice is to use this nature to our benefits. Isa yan sa mga factors na kinukonsider sa building water system. Pressure difference from elevation change or what we call static head. In the building plumbing supply system, water is the fluid under consideration. Water has a maximum specific weight of 62.4 pounds per cubic feet. Tandaan po natin yan. So, at its maximum weight, 1 feet by 1 feet by 1 feet cube of water exerts a maximum force of 62.4 pounds at its base, which equates to a pressure of 62.4 pounds per square feet, or a pressure of 0.433 psi at the base of the cube, or 62.4 pound per square feet divided by 144 square inches by square feet, 0.433 pounds per square inches. Therefore, a 1 feet high column of water creates a pressure of 0.433 psi at its base. A 2 feet high column exerts a pressure of 0.866 psi at its base, because 2 times 0.433 psi. A 3 feet column, 12.99 psi at its base, 3 times 0.433 psi, and so on. In a plumbing supply system, pressure difference from elevation change, or simply static head, is found by multiplying the vertical height Z in feet by the factor of 0.433 psi per feet. By convention, the vertical height is positive if elevation increases from the station with the known pressure, the station is higher than the station with the known pressure, and negative if elevation decreases. Yung positive po natin, magkukos po ito ng downward motion. While itong pag nagne-negative po siya, magkukos naman siya ng upward motion sa tubig po. Tapos, tandaan po natin na yung 0.433 PSI per feet is equal po siya sa 9.795 kilopascals per meter. Equal lang po siya. Pressure difference is negative or a loss if the elevation change from the known pressure is upward. Yun na nga po yung sinasabi ko kanina na nagiging negative po siya kapag pataas po ang motion ng tubig. And positive if elevation change is downward. Nagpa-positive naman po siya kapag pababa ang motion ng tubig. It means pag pataas, galing po siya sa mababang area papunta sa mataas. Kapag pababa naman, galing siya sa mataas papunta sa mababang area. Pressure change in plumbing system from elevation change may be computed by multiplying the vertical height of the fixture outlet to the street main. A known pressure by the pressure the water creates per foot. Conversely, a 2.31 feet of elevation change results in a pressure difference of 1 psi and a 0.102 meter change results in a pressure difference of 1 kilopascals. Kasi po, 2.31 feet times 0.433, cancel po yung 2 feet dun sa units na ibinigay. Then, kakalabasan po nun is 1 psi. Then, multiply naman po natin yung 0.102 meter dito sa 9.795 kilopascals per meter. Makakancel po yung yung unit natin. Ang matitira po is kilopascals. Kaya, ang pressure difference is 1 kilopascals. 1 kilopascal. Next is pressure loss from friction. Pressure losses from friction or friction head are more difficult to compute as they are related to flow rate, fluid velocity, pipe diameter, pipe material, and surface roughness, pipe length, and number of fittings and valves. So, experimentation has led to a variety of pressure drop charts for pipes of many different materials. Let's proceed now to water supply design concern. Water velocity, noise, erosion of inner pipe walls and valves, and economy of installation, operation, and maintenance dictate the minimum and maximum water velocity in a plumbing system. As a result, these have a bearing on pipe diameter. If pipe diameters are small, cost is low, but noise, erosion from high velocities, and pumping costs from high pressure losses are high. In contrast, large diameter pipes reduce noise erosion and pumping costs, but result in high installation costs. An intermediate pipe diameter is desirable. If the diameter of the pipe is small, expected po natin na low cost ito, pero maraming factors ang makaka-apekto rito. The pipe will be prone to noise, erosion from high velocities, and pumping cost from high pressure losses, at yun ang mga factors na dapat nating iwasan sa plumbing system. Kapag masyado namang malaki ang diameter ng pipe, although mababawasan ng noise erosion and pumping cost, magre-resulta naman yun sa mataas na gastos sa installation. So, kaya dapat ay intermediate lang ang size ng pipe na gagamitin natin. Balance lang po dapat tayo. Typically, plumbing codes set velocity limits in water supply piping. Maximum water velocities in plumbing water supply piping are usually limited to a range of 5 to 10 feet per second, 1.5 to 3 meter per second. Maximum velocities of up to 15 feet per second or 4.5 meter per second are allowed for equipment feed lines in mechanical rooms. Example, boiler feed lines, where noise is less of a concern. The maximum safe velocity for thermoplastic pipe is about 5 feet per second or 1.5 meter per second. Cavitation is a physical phenomenon that occurs in a liquid when it experiences a drastic drop in pressure that causes the liquid to vaporize into small vapor bubbles. Vaporization is a problem because the liquid being vaporized expands greatly, lumalaki. For example, 1 cubic feet or 1 cubic meter of water at room temperature becomes 1,600 cubic feet or 1,600 cubic meter of vapor at the same temperature. As the low pressure returns to normal pressure levels, these bubbles implode as the vapor changes phase back to a liquid and thus drastically decreases its volume. This implosion causes noise and high levels of erosion. Mga factors po na alam naman nating nakakasira or harmful sa pipes natin, where the imploding bubbles contact the walls of a pipe, fitting, pump, or valve. The noise that develops sounds similar to gravel flowing through the system in the area where the cavitation is developing. Over time, the erosion results in excessive wear. This eventually manifests itself as pinhole leaking. Ito po yung worst case scenario natin. Kapag nangyari to, get ready na po tayo para sa gastusin for repair and installation. Valves can develop cavitation when they are partially closed and flow is restricted. The result is noise and possible damage from erosion. Cavitation can also develop in a pump, which is noisy and can adversely affect pump performance by causing violent and damaging vibration and a sharp drop in discharge pressure. It occurs if the pump liquid on the suction side of the pump drops below its vapor pressure. Eliminating this potential for cavitation is necessary because a cavitating pump can be completely damaged in a few hours of operation. Yun nga po, hindi lang pipe ang prone sa cavitation, maging ang valve and pump po natin ay pwede ring magkaroon ng cavitation. So, similar po sa cavity sa ngipin na nagpapahina tapos nagpaparupok dito hanggang sa tuluyan ng madamage ang ngipin, same din po ang effect ng cavity sa plumbing system. In short, it's very harmful. So, sa cross connection na po tayo. A cross connection is an unsatisfactory connection or arrangement of piping that can cause non-potable water to enter the potable water system. A cross connection can cause used or contaminated water to mix with the water supply. It is an unsanitary and potentially hazardous condition. Sa cross connection, it is a big threat to public health and safety. Just imagine yourself drinking a poison from your faucet. Diba, kita naman natin kung gaano kalala magiging epekto nito sa kalusugan ng tao. Remember po natin na most of illnesses are caused by unsanitized drinking water system. So, at most cases, ito po ang pinaka-iniiwasan na mangyari in plumbing works. So, most plumbing fixtures are designed to prevent a cross connection. A gap exists between the faucet and the rim of the bowl in lavatories, sinks, and tubs to create a separation and avert a cross connection. An air gap is the vertical distance through open air between an opening in a fixture or faucet conveying potable water to the flood level rim of a tank or fixture. As a general rule, the minimum air gaps for cross connection protection for fixtures against one walls are as follows. Nandiyan na po sila, nakasulat na sa baba. So, ito po yung mga method to avoid cross connection. Kailangan po nating bigyan ito ng pansin as stated din po sa plumbing codes and regulations natin. Air gaps must be increased if the lavatory sink or tray is against two walls instead of one. Building codes will cite the minimum air gap based on fixture type. This is typically 2 times the inner diameter of the pipe to the inside serving the fixture. Backflow is a type of cross connection that occurs when contaminated water or some other liquid or substance unintentionally flows backwards into distribution pipes containing potable water. Simply, it is water flowing in the opposite direction from normal flow. So, ibig sabihin ay nagmamalfunction ang system natin. So, backflow can allow contaminants to enter the potable drinking water system through cross connections. Related po yung dalawa sa isa't isa. Back pressure or back siphoning is backflow caused by a negative pressure or what we call vacuum in a potable water system. A downstream pressure that is greater than the supply pressure causes back pressure backflow. A backflow can be avoided by the use of proper protection device. Backflow prevention protects the potable water system from minor, moderate, and severe hazards. A backflow prevention device, often called a vacuum breaker, is a device or plumbing assembly that when properly installed in a plumbing system, prevents backflow. At ganun nga, so kapag may problema, meron ding prevention method. Vacuum breaker can prevent the backflow in a plumbing system, and that's a good thing thanks to vacuum breaker. Next, water hammer. A large pressure develops when fluid moving through a pipe is suddenly stopped in a plumbing supply system. The sudden closing of a valve will cause fast-flowing water to stop quickly, resulting in a large increase in pressure that is known as water hammer. To avert water hammer damage to a building's plumbing system, air chambers or water hammer arrestors are used in the supply branches serving each fixture. These devices are use trapped air to cushion the hydraulic shock. Like sa backflow, water hammer can also be prevented by using air chambers or water hammer arrestor that trap air to cushion hydraulic shock. Need lang nating maging aware sa mga concerns din, solution needed, tapos ang devices na ginagamit for remedy. Ito po yung mga definition niya. Air chamber. Air chamber are 15 inches to 5 feet long pipes or pipe-like devices. They are installed vertically above the fixture water connection and are concealed in the wall. Air is trapped within the air chamber. The trapped air is compressible, which cushions the pressure surge as the valve is closed and absorbs the hydraulic shock. Next is water hammer arrestor. Water hammer arrestor are patented devices that absorb hydraulic shock. Such devices, when installed, must be accessible for maintenance. One type should be placed at the end of a branch line between the last two fixtures served. Additional arrestor should be placed at the midpoint of a run longer than 20 feet. Meron po tayo ditong pictures. Yan po, water hammer arrestors, yung dalawa pong nakausli na bakal. Above shut off valves at a clothes washing machine connection. Thermal expansion. No matter what type of piping material is used in the water system, some expansion in the pipe will occur. This expansion must be considered in the design of the system. The amount of expansion will depend on the type of piping material and the range of temperatures that the pipe will be subjected. So, thermal expansion. Expansion of copper tubing is slightly greater than 1 inch in a 100 feet length in a 100 degree Fahrenheit temperature change. Yung plastic pipe will expand even more, up to 10 inches in a 100 feet length in a 100 degree Fahrenheit temperature change. Thermal expansion in the pipes of a plumbing system must be accommodated to minimize damage from thermal movement. Expansion from temperature increases can push a pipe through a wall or cause it to burst. There are two methods in common use for providing for expansion in pipelines: expansion bends and expansion joints. So, ito po yung mga illustration. Expansion bend. Ganun po siya. So, sabi dito, types of expansion bends and loops. Thermal expansion in the pipes must be accommodated to minimize damage from thermal movement. Dako na po tayo sa viscosity. As water flows through a pipe, its viscosity or what we call thickness decreases with temperature decrease. Water at 40 degree Fahrenheit or 4 degree Celsius is twice as viscous as water at 90 degree Fahrenheit or 32 degree Celsius, and 4 times as much as 170 degree Fahrenheit or 77 degree Celsius. As a result, pumping energy and cost are higher when water temperatures are lower. Tandaan lang po natin na ang viscosity is directly proportional to the temperature and inversely proportional to the pumping energy and cost. Means na mas mababa ang temperature, mas mataas ang pumping energy and cost. Okay po, ulitin ko, mas mababa ang temperature, mas mataas ang pumping energy and cost. Next is volume change with temperature change. Water is the only substance that can exist as a solid, liquid, and gas at ordinary temperatures. Like most substances, water expands when it is heated. Unlike most substances, the volume of water increases when it freezes. Below 39 degree Fahrenheit or 4 degree Celsius, water molecules begin to align themselves into the crystal structure of ice, causing its volume to increase slightly. Under normal conditions, water freezes at 32 degree Fahrenheit or 0 degree Celsius. It expands significantly when the molecules of water are pushed farther apart than they were in a liquid state. So, alam na natin to. State of matters lang. Kapag nag-start mag-crystallize ang water, medyo lumalaki ang volume nito. Example, yung ice water sa rep. Opo, yung ice water sa rep. At kapag naging yellow ito, pansinin natin na nagiging bulky ito ng kaunti, di ba? Ganun lang yun. Mas lumalaki ang volume niya. Next is freezing. A phase change from liquid or water to solid or ice results in about a 10% increase in volume. 10% increase in volume. A pipe fitting or tank filled with water can burst if the water is exposed to below freezing temperatures, even for a short period of time. A burst pipe will typically result in flooding that can cause catastrophic damage to the building and its content. Flooding may occur as the water freezes and bursts the pipe or after the frozen water toss. So, sa freezing, ganun nga. Tumataas ang volume niya, then may exact percentage na naibinigay, about 10% daw. Magre-resulta yon sa burst pipe, then flooding ng kasunod. Next is expanding water. Liquid water expands about 39 degree Fahrenheit or 4 degree Celsius. Expansion is about 4.37% from 40 degree Fahrenheit or 4.4 degree Celsius to 212 degree Fahrenheit or 100 degree Celsius. This volumetric change from expansion or delta V equates to about 0.0254% per degree Fahrenheit or 0.0457% per degree Celsius. In any piping system, provisions for expansion and contraction of liquid water must be considered. So, in an open plumbing system such as building water supply system, pressure build up from thermal expansion of water is released each time a faucet or valve opens. Pagkatapos ay i-release na ang mga excess pressure into the surrounding air. Ganun lang po. Steam. Under standard atmospheric pressure, may mga unit na binigay, the boiling point temperature of water is 212 degree Fahrenheit or 100 degree Celsius. Water boils and is converted to steam at its boiling point temperature. So, nagkakaroon ng change about 160,000% increase in volume yon, or an increase of 1,600 times. Although steam is not found in building plumbing systems under ordinary conditions, a faulty water heating appliance such as a boiler or domestic water heater may result in the development of steam. Example, a water heater with defective thermostatic controls which can have catastrophic results. So, itong steam, di naman siya gaano makikita sa plumbing system, pero need pa rin po natin maging aware dito. Aging. As pipes in a plumbing system are used, their inner walls become increasingly rough. The effects of aging in a plumbing system are related to piping material, quality of water, example, hard versus soft, and water temperature. Build up from calcium deposits, especially in high temperature hard water, and corrosion, especially in ferrous pipe materials, reduces the inside opening in the pipe, which restricts flow. Over several decades of use, aging galvanized steel and iron pipe can result in a capacity loss of up to 80%. Copper piping experiences about half the capacity loss from aging as do steel and iron pipes. Plastic pipes experience little loss of capacity as they age. Aging means naluluma na. Natural lang naman na maluma mga bagay once na ginagamit mo sila. Pero at least, dapat alam natin yung properties ng mga materials natin. For example, plastic pipes ang pinakamatagal maluma kumpara sa mga copper, steel, and iron. So, best choice, plastic. Pero may mga circumstances din na mas magandang choice ang ibang materials or depende sa availability ng materials. Next is pipe insulation. Pipe insulation is applied to the outer walls of piping to reduce heat loss from the pipe or prevent condensation on the outside pipe walls. Foam and covered fiberglass insulation are common pipe insulation materials. Yung hot water supply lines, especially on hot water recirculating system, should be insulated to reduce heat loss and save energy. In most commercial buildings, heat loss increases the cooling load and the cost of air conditioning. In residential applications, in temperate to cold climates, insulating hot water lines is less cost effective because heat loss from hot water pipes contributes to space heating during the heating season. That is, the heat loss is extremely small. So, pipe insulation is all about minimizing heat loss of hot water supply para daw mas makatipid tayo. Kaya, iba't ibang techniques na lang gagamitin para sa goal na to. Yung goal na makatipid, to save energy. So, next is testing. The water supply system should be tested for leaks before it is covered with finished materials to determine if it is watertight. Tests commonly run on water systems require that it be watertight under a hydrostatic water pressure of 125 psi for a minimum of 1 hour. Any leaks that occur should be repaired with the joint compound originally used. Yes naman, we need trials before the actual thing para masiguro na safe at de kalidad. We need to test it first. So yun nga, test must always be done. Leaks. Surprisingly, plumbing leaks contribute significantly to water consumption in operating plumbing systems. Leaks not only waste money and water, they can cause damage to walls, flooring, ceilings, furniture, and electrical systems. Leaking pipes also create an environment for mold and mildew to thrive. Water damage claims may result in a building owner's insurance premiums being raised or non-renewal of policies. Leaks can develop from substandard piping, improper use of materials, poor workmanship, and improper design. Madami ang consequences kapag nagkakaroon ng leaking kaya we must prevent this at all cost para di na lumala pa. Kapag may leaks, repair agad. Huwag manghinayang sa repair cost kasi mas manghihinayang ka kapag mas lumala pang sitwasyon. Mas maraming problema, mas maraming gastos. So, to sum it up, there are plenty of things we must consider in building water system, especially in plumbing system. May mga factors na dapat iwasan at may mga guidelines din naman na dapat isaalang-alang. So, thank you for listening. That's the end of my part.
Water supply pipe design methods. First is flow rates. Flow rate will vary by type of fixture and water pressure at the fixture. Each fixture in a plumbing system is designed to operate at a specific flow rate, expressed in gallons per minute (GPM), liters per second (LTS), or liters per minute (L per minute) of flow. Residual water pressure available at the outlet before a fixture affect the flow rate of a fixture. A higher pressure results in a greater flow rate and thus more water consumption. Flowing fluids are characterized by a quantity called the flow rate, which is defined as the volume of fluid flowing through an area each second. Flow rate can be expressed in terms of fluid speed and the cross-sectional area of the pipe. The second is water consumption. Water consumption is the portion of water used that is not returned to the original water source after being withdrawn. For example, irrigated agriculture accounts for 70% of water used worldwide, and almost 50% of that is lost, either evaporated into the atmosphere or transpired through plant leaves. Water consumption is the portion of the withdrawn water permanently lost from its source. This water is no longer available because it evaporated, got transpired, or used by plants, or was consumed by people or livestock like irrigation is by far largest water consumer. Then the third is water demand. The instantaneous peak demand for water in a pipe serving a number of plumbing fixtures or serving an entire building is referred to as the design load. The design load is the maximum probable or peak instantaneous demand for domestic water by a group of fixtures. The design load is typically expressed in GPM, L per minute, or liter per second rather. The design load of a pipe serving a group of plumbing fixtures or for the total fixtures installed on a project will depend not only on the number and type of fixtures installed but on the operation of fixtures. Some fixtures may at the times have continuous flows, etc., faucets, hose bibs, and shower heads, while other fixtures have on intermittent flow, etc., water closet, and urinals. Water demands includes water delivered to the system to meet the needs of consumers, water supply for firefighting and system flushing. Simple empirical design method. Pipe sizes for the water supply system of a single family house and similar simple structure can be determined on the basis of experience and pertinent code requirements. Detailed analysis is not necessary in the design of simple system. The fixture fed by the branch will influence branch pipe diameter. Pipe diameter is determined by the pipe size serving the fixture. In the empirical design method, piping is sized with rules of thumb based on observation and experience. For example, the mains that serve fixtures branches can be sized as follows. It is a method which is based on the results of experience or experiments, etc., that like loads, materials, layer configuration, and environment, and pavement failure were arrived at through experience, experimentation, or a combination or both. Then empirical design as applied to the structural design of buildings is the application of proven sizes, proportions, materials, and assemblies. Fixture unit. A method of estimating the design load for a group of plumbing fixtures is typically based on a quantity called the fixture unit. The fixture unit is an arbitrarily chosen measure that allows all types of plumbing fixtures to be expressed in common terms. That is, fixtures having twice the instantaneous flow rate of a second fixture would have a fixed unit value twice as large. The solve for force of the mixed fixtures unit concept is to make it possible to calculate the design load on a system composed of different types of fixtures, each having different flow rates. It's a unit of measure based on the rate of discharge, time of operation, and frequency of use of a fixture that express the hydraulic load imposed by the fixtures on the sanitary plumbing installation. Fixture unit is used in plumbing design for both water supply and wastewater. Then next is method 2, WSFU design table method. In residential and small commercial buildings, WSFU design tables can be used to establish meter and distribution pipe size based on the total demand in WSFU and the supply pressure, the available static pressure after static head loss. Method 2, WSFU design table method, is the standard method for estimating in the water demand for a building. Meter and distribution pipe can be sized using the following methods. First is obtain minimum service water pressure for the location of construction. Usually this is available through the municipal waters department. Then the second is compute the total WSFUs, including for proposed and project future plumbing fixtures. The third is calculate the maximum developed length of water piping, the actual length of pipe between the source of supply and the most remote fixture plus the developed length of fittings. Developed length can be approximated by multiplying the actual length to the most remote fixture by 1.2. Compensate for loss of meter and fittings. Meter and distribution pipe can be sized using the following methods. Of course, compute the static head, the pressure loss from elevation change, and subtract it from the service water pressure, static head. PS static is found by multiplying the vertical height Z in feet or meters. Static head in PSI. PS static is equals to 0.33 Z. Static head in kVA. Triangle PS static equals to 9.87 Z. Meter and distribution pipe can be sized using the following methods. Use the table on the next slide to differentiate the meter and distribution pipe sizing based on the total demands in WSFUs, maximum developed length of water piping, and the supply pressure, the available static pressure after static head loss, maximum water supply fixtures unit, WFSU for a supply pressure, the available static pressure after head loss, and a specific pipe size. Method 3, velocity design method. So the velocity design methods entails selecting the smallest pipe diameter without exceeding a pre-established maximum velocity for the design load in the pipe. It is typically used accurately in a downfeed system and works well in preliminary design of a plumbing system provided the system layout is reasonably symmetrical. This method thus required an investigation of pressure loss to ensure that residual pressure at the most remote fixture is adequate. It is used accurately in a downfeed system and works well in preliminary design of plumbing system provided the system layout is reasonably symmetrical. So next is method 4, equal friction design method. A more accurate approach to sizing the pipe diameter in a complex network of pipes is the equal friction design method. In this design method, it is necessary to determine the total pressure drop required between the water and service and the fixture and equate this is to a pressure drop per 100 feet over the equivalent length of pipe. Pressure available at the water service minus pressure head and desired pressure at a fixture determines the desired pressure drop. This method is more complex and more accurate but usually requires several iterations before pipe diameters are selected. So method 4 is equal friction design method. It is the more accurate approach to sizing the pipe diameter. So next is water temperature. Cold water. The temperature of water available in the water supply system will vary. Water from shallow, just below frost line, underground water service line enters the building at a temperature that fluctuates with climate season and location of the water service line. In a moderate climate, it may range from 35 degrees F and times to 2 degrees Celsius in midwinter to 70 F and 21 degrees Celsius or more in midsummer. In hot climate regions, water service temperature can be reached temperature above 90 degrees F then 32 degrees Celsius IC or more in the summer. In harsh desert climates, water must actually be chilled for drinking. Cold water is generally between 80 and 60 F, then 26.7 to 15 degrees Celsius. Chilled water is desired such as from a drinking fountain. Then next is chiller is a vapor compression. Refrigeration system that cools water much like a refrigerator. Heated water. In modern buildings, hot water is desired for bathing, cleaning, washing, and other associated purposes. By definition, hot water is potable water that is heated to at least 120 degrees F. Heated water below 120 degrees F. 49 degrees Celsius is typically cold temperature water. Hot water used for household functions such as bathing, dishwashing, and clothes washing is referred to as domestic hot water, THW. In a commercial installation, hot water used in non-domestic application is referred to as building service hot water, BSHW. The temperature of heated water available in water supply system will vary depending upon need. Tempered water is a blend of hot and cold water that is mixed at a thermostatic mixing valve. It is used in application requiring low temperature hot water. Typical application includes shower rooms and group showers, domestic water for small buildings, and tempered water for light industrial process, etc. Photographic laboratories. The temperature required for the tempered water typical range from 90 degrees to 110 degrees F, 32 degrees to 43 degrees Celsius. Using the mixing bulb is set at the desired temperature and delivers water within positive negative 3 degrees F, positive negative 1.7 degrees Celsius. C. The temperature setting. An anti-scald shower valve is type of thermostatic valve required in residential showers. This valve can be preset to any temperature between 60 degrees and 120 degrees F and 15.5 degrees and 49 degrees C Celsius with flow rates between 0.5 GPM and 10 GPM, which ensures the safety equipment. Safety receivers receive water at required temperature. It consists of three major components. First is a hot water storage tank, and the second is a heater, and the last is the bleeding valve. Domestic water heating. Types of water heater. Water heater is an appliance or system that heats water for domestic or building service hot water use. There are three types of water heaters: storage tank water heaters, instantaneous on-demand tankless water heaters, and circulating water heaters. Different types of water heaters like a residential storage tank water heater. Yan siya, medyo maliit lang siya pero kikita mo naman yung design niya. Then a gas connection to a residential storage tank water heater. Note the drain valve on the right side of the tank. Next is plumbing connection to a residential storage tank water heater. The electric unions are used to minimize a galvanic reaction between the copper pipes and the water heater. Shared storage tank water heater. Then next is a commercial gas-fired storage tank water heater. Then a commercial electric storage tank water heater. Note the presence of an electric connection and lack of presence of a vent. 2. Dry-efficient, gas-fired, powered, vented storage tank water heaters connected in series. Note the drain pans at the base of each unit that are designed to drain water into a floor drain. So next ng heaters natin is gas-fired, instantaneous water heater. Then a water heating boiler that provides hot water to a commercial building. A storage tank water heater consists of a storage tank and a heating medium. Typically, storage tank size include 30, 40, 50, 60, 65, 75, 80, 100, and 120 gallon, 120 to 400 liters capacity niya. They are available in natural gas, propane, LP, fuel oil, and electric models. Storage tank water heaters remain the most popular type for residential heating needs in the United States. An average size 3-bedroom residence uses a 50 gallons per 200 liter water heater. Electric water heaters have coil-like elements that extend into the tank, which heat water as electric current passes through the elements. Gas and fuel oil-fired water heaters have burners located on the bottom of the tank and a vent that passes up through the center of tank rather. Types of storage tank water heaters include the following. Residential storage tank water heaters are designed for the residential market but can be appropriate for many small commercial facilities. These water heaters, which are available with tank sizes up to 120 gallons and gas inputs up to 75,000 BTU per hour, are manufactured in large quantities. As a result, they are relatively inexpensive and widely available. Commercial storage tank water heaters are similar to residential models, except that they are available with much higher gas input ratings, 1 million BTU per hour or more, and larger storage tank up to 250 gallons. They also feature larger pipe connection, more rouge control, and a few features that are only rarely found in residential heaters, such as flue dampers and electronic ignition. Types of storage tank water heaters include the following. Ultra-efficient water heaters use power burners and enhanced heat exchangers to force hot combustion gases into chambers and tubes that are submerged in the storage water. Ultra-efficient water heaters are vented with plastic pipes that go directly through an outside wall because they draw combustion air directly from outside through one of those pipes. The combustion processes are sealed off from the occupied space. Spontaneous water heaters, sometimes called tankless water heaters or demand water heaters, supply hot water on demand. They do not rely on a standby storage in a tank to artificially boost their capacity. Instead, they have a heating device that is activated by the flow of water when a hot water valve is opened. Once activated, the heater delivers a constant supply of water. The outputs of the heater, however, limits the rate of the heated water flow. They are more efficient because they do not have any standby losses. Instantaneous water heaters are available in natural gas, LP, and electric models. They come in a variety of sizes for different applications, such as a whole house water heater, a hot water source for a remote bathroom or hot tub, or as a boiler to provide hot water for a home heating system. Circulating water heaters. Circulating water heaters consist of a separate storage tank that stores water heated by a heat exchanger. The heat exchanger may be a separate unit that is heated by steam or hot water from a boiler, or may be contained in a boiler. The boiler may be designed to exclusive heat water for DHW or BSHW use, or may be used for other purposes. So next is tankless coil and indirect water heaters. A building space heating boiler can also be used to heat water. Two types of water heaters that use this system are tankless coil and direct. No separate storage tank is needed in the tankless coil water heater because water heated directly inside the boiler in a hydraulic hot water heating system. The water flows through a heat exchanger in the boiler whenever a hot water faucet is opened. During colder months, the tankless coils work well because the heating system is used regularly. However, the system is less efficient during warmer months and in warmer climates. When the boiler less efficient during warmer months is used less frequently or not all. That is, the boiler must operate when hot water is needed. Then, a separate tank is required with an indirect water heater. Kikita nyo na lang po sa figure. Like the tankless coil, the indirect water heater circulates water through a heat exchanger in the boiler. But this heated water then flows to an insulated storage tank because the boiler does not need to operate as frequently. This system is more efficient than the tankless coil. In fact, when an indirect water heater is used with a highly efficient boiler, the combination may provide one of the least expensive methods of water heating. Next is heat pump water heaters. Heat pump water heaters extract energy from outdoor air and use it to produce hot water very efficiently. Heat pump water heaters use an electric motor to run a compressor. The compressor draws a gaseous refrigerant through an evaporator, raising its pressure until it liquefies in the condenser. This heat pumping process heats the condenser and cools the evaporator in removing heat from air. The heat pump both cools and humidifies the air, thus helping to also meet cooling needs. The heat pump water heater makes economic sense in hot, humid regions where natural gas is unavailable. Tropically island like Hawaii, electric energy cost is high and the need for the humidification is virtually constant. Next is a solar water heaters. A solar water heater typically includes collectors mounted on the roof or in a clear area of the yard. A separate storage tank near the conventional heater in the home connecting pipes and an electronic controller. Throughout the year, the solar system preheats the water before it reaches the conventional water heater. Solar water heating system can reduce the annual fuel cost of supplying hot water to a residence by more than half. There is, however, the added cost of the solar system. Next is the superheaters. The superheaters is an attachment to an air conditioner or heat pump that allows waste heat from the device to assist in heating domestic water. In hot climates, the superheater can provide most of homes' hot water needs. Next is energy efficiency. The energy factor EF, energy efficiency, used to express the efficiency or residential heaters. It was developed by the U.S. Department of Energy. It represents the amount of heat required to warm up hot water for a typical home in a year, divided by the amount of energy input into the heater to warm that water. A water heater with an EF of 0.60 transports 60% of the energy it consumes to the hot water. The remaining energy is vented outdoors as waste heat. The higher the EF, the more energy efficiency the water heater and the less energy consumed. Hot water circulating system. In many medium and large commercial buildings and even some residences, a hot water recirculating system continuously circulates hot water from the water heating unit through the hot water supplying piping and back to the water heater through hot water recirculating piping. This ensures that hot water is always available at the taps, thus avoiding the need to run water for a long time to obtain water at the desired temperature. There are three types of water recirculating strategies as follow. First is continuous recirculating, time recirculating. Then the third is thermostatically controlled recirculating. Continuous recirculating. In continuous recirculating, water is constantly recirculated from the water heater through the piping. This type of system is best suited for buildings having round-the-clock occupancy, hospitals, and multi-unit residential buildings typically require continuous hot water recirculating. Time recirculating involves use of an electronic or electromechanical timer to shut off circulation of hot water when the building is not occupied. This shutdown would apply to commercial, institutional, and industrial buildings that are closed at night and or on weekends. Nighttime housekeeping and maintenance operations should not be neglected when considering shutdown periods. Thermostatically controlled recirculating. Thermostatically controlled recirculating relies on a sensor located at a remote location in the recirculating line, which senses water temperature and activates the circulating pump when water temperature drops below a predetermined setting. Small to medium-sized buildings typically have a single recirculating loop, recirculating pump, controls, and water heating system with storage tank. In large buildings, several recirculating loops may be necessary. Each loop will typically have its own piping and controls. One recirculating pump will usually serve all loops with balancing bulbs controlling flow to a specific loop. The pump requires a minimal horsepower drive in the range of 1.5 or 1/16 HP, just enough to keep the water moving. To reduce heat loss, the hot water recirculating piping must be insulated. Design load. Hot water use is not spread out over the entire day. Instead, domestic use of hot water tends to peak in the morning hours and again in the early evening, super time. As a result, a water heating system must be designed to have sufficient capacity to provide hot water during periods of peak use. An accepted method of determining The maximum demand on a water heater is to determine peak usage during a particular time of day. For single and two family dwelling units, this peak occurs during the morning or early evening. Sizing storage tank water heaters. Residential water heaters are typically sized based on their first hour rating FHR. This rating is contained on the US Determine of Energy Guide label found on all water heaters. The FHR relates to the gallons of hot water available for 1 hour of peak demand. It is maximum output of the water heater over an hour in gallons of water in a 100% of temperature rise. The FHR is the sum of the standby hot water found in the tank plus the capacity of the heater to heat water during the first hour. Typically, standby water is taken as 70% of the tank capacity. FHR in a gallons is equals to 70% of tank capacity per gallons plus recovery rate gallons per hour.
Water supply system design. Demand loads consist of three steps. First is we need to determine the demand load through listing the fixture. It includes 4-story apartment building, 3 inches or 75 millimeter service main, street main pressure 50 psi or 345 kPa. Fixture per floor: 2 flash bulb water closets, 2 tubs with shower heads, 2 lavatories, bathroom sinks, 2 kitchen sinks, 4 hose bibs on the first floor, 3 8-inch 10 millimeter supply general use. It should be noted that at this point, the apartment building being sized for the water system has a repetitive floor plan for each floor. This allows the entire apartment to be serviced from a single water pipe riser going up the building. As you can see in the picture, on the left side of the apartment, the water riser are both located on the side of the hallway. On the right side, water riser is located at the wall. The elevation of water riser in apartment building zone, as you can see in the picture on the left side. And on the right side is the water zoning consisting of upfeed and downfeed. The next step in demand load is the WSFU demand for each floor and the entire apartment building is found. Total fixture units per floor: 2 bathroom groups, flash bulb, private. 2 kitchen sinks, 20 WSFU per floor. Apartment fixture units per on riser: 20 WSFU per floor times 4 floors equals to 80 WSFU. Additional fixture unit: 2 hose bibs. First floor: 2 WSFU times 2 equals to 4 WSFU. Total fixture units on the riser: 80 WSFU apartment plus 4 WSFU hose bibs equals to 84 WSFU. The third step is the demand for the water in gallons per minute can now be determined by using the table 13.9 for various WSFU loads. As you can see, here is the conversion. In this part, the pipe sizing is very important in order to attain the needed pressure for water to rise up and be scattered throughout the apartment's street. Main pressure must be accounted and adequate supply. Here is the accumulated information. The first step in sizing the main supply is to determine the pressure losses. The pressure loss from static head is computed by multiplying 0.434 psi per feet or 9.8 kilopascal per meter times the vertical distance of the riser from the service main into the building to the top branch water line. Static head loss change in pressure static equals to 0.434 psi times 40 feet equals 17.36 psi. In metric units, static head loss change in pressure static equals to 9.8 kilopascal times 12.2 meters equals 120 kilopascal. The residual pressure required at the most remote fixture on the top floor must be determined. The design should also leave some excess pressure so that more than one fixture can be operated properly at the same time. The pressure loss from the fixture in the main riser pipes, the fittings, and the meter must be found next. Add the static head and the pressure required for the most remote fixture. Then subtract the total from the available street main pressure to find the pressure left, which is the maximum amount that can be lost to the fixture. Street main pressure 50 psi, static head plus fixture pressure 17.36 plus 15, negative 32.36 psi. Pressure left to overcome friction 17.64 psi. Residual pressure available in metric unit. Street main pressure 345 kPa. Static head plus fixture pressure 120 plus 100 equals to negative 220 kilopascal. Pressure left to overcome friction 125 kilopascal. Residual pressure available for the water closet is acceptable. 4. Sizing the piping using equal friction design method is a matter of trial and error. The process involves first selecting a pipe size for the building main which runs from the water system to the riser, and then determining the friction loss for the pipe used from friction loss chart. The chart used will depend on the type of pipe used. From the friction loss chart, the first pipe, size 59 servicing GPM in 4 inch. Because this is much larger than the street main, keep moving to the right and 21 hubs in pipe, where the horizontal line from 59 GPM touches the line representing 21 hubs in. Draw a vertical line to the bottom or top, and the friction loss reads about 1.26 psi per 10 per 100 feet. For the other pipes, the following friction reading are taken. This is the result. In metric units, from the friction loss chart, going to the left side to the right, the first pipe size servicing 3.72 liters per second is 100 millimeter. Because this is much larger than the street main, keep moving to the right to a smaller pipe 65 mm, where the horizontal line from 3.72 liters per second touches the line representing 65 mm. Draw a vertical line on top. The friction loss reads about 28.4 kilopascal per 100 meters. From the other pipes, the following friction reading are taken. This is the reading. Because all friction losses are given per 100 feet of pipe length, the distance from the street main to the base of the riser must be checked on the plot plan. Referring to the Appendix A, the horizontal building main distance estimated about 60 feet. So, for example, the friction loss in the building main pipe will be 60, 100, 3, 5, 0.6 or 60% of the values recorded. Friction losses for 60 feet of pipe are as follows. This is the reading again. By observation, The one in pipe is eliminated because its friction loss is slightly greater than the friction left in the calculation, 17.64 psi. The 11/4 inch, 11 halves inch, and 21 halves inch pipe are all possibilities at this point. In metric units, referring to Appendix A, the horizontal building main distance is estimated at 18.3 meters. So for this example, the friction loss is in the building main pipe will be 18.3 100 or 18.3% of the bus recorded. Friction losses for 18.3 meter of pipe are as follows. This is the reading again. By observation, the 25 millimeter pipe is eliminated because its friction loss is higher than the pressure left for friction loss in the calculation, 125 kPa. All of the other pipes are still possibilities at this time. Number 5. The next step is to determine the pressure loss as the water passes through the meters. When the main size is 11 halves inch or greater, the most common main meter selection will have meter 1 size smaller than the main. For this problem, locate the GPM along the bottom, in this case 59 GPM, and go vertically to the first diagonal line, 3 inches. At this point, move horizontally to the pressure loss reading. This is the reading. Totaling the pressure per main and meter. Just add the two readings. In metric SI, totaling the pressure from the main. Add again. Referring back, there is a pressure of 17.64 psi left to overcome the pressure loss from friction in the main, meter, and riser. The total above are pressure loss for the main and the meter. The riser pressure loss must still be calculated. Because the most economical solution involves the use of smallest pipe size, which are provide an adequate flow of water throughout the system, at this point a preliminary selection of 21 halves inch pipe and 11 halves inch meter is made. This means that the 17.64 psi that are left to overcome the friction, 10.46 psi will be used in the 21 halves pipe and 11 halves inch meter. This leaves 7.18 psi as the maximum friction loss in the riser. Using a 2-inch main and 11 halves inch meter would leave 17.64, 11.62, 6.02 psi for riser friction. Using 21 halves in main and 2-inch meter would leave 17.64, 4.56, 13.08 in metric unit. This is the result. Using a 50 millimeter main, a 40 millimeter meter would leave 125 minus 80.1 equals to 44.9 kilopascal per friction loss. Using the 65 millimeter main and 50 millimeter meter would leave 125 minus 31.4 equals to 93.6 kilopascal. The next step is to select the possible pipe sizes for the riser. Using the friction loss pipe chart, find 40 GPM flow in the side. The following friction loss readings are taken. Once again, note that the friction losses are given per 100 feet or 100 meter of pipe length. This means that the vertical distance from the main to the highest is the most remote fixture must be estimated. On some projects, this may mean meeting with the architect as certain floor-to-floor height. For this apartment building with floor-to-floor heights of approximate 10 feet to 0 inch 3.0 meter, the overall riser height will be approximately 40 feet. In such piping, there is an additional friction loss per fitting. When the entire system has been designed and all pipe sizes are fitting located, it is possible to determine the friction loss per the fittings. An example on how to calculate fittings provided in pressure losses from friction. Because during this stage of design, the fittings have not determined. It is common practice to allow an additional 50% of piping length to account for the friction loss in the fitting. In this case, the pipe length is 40 feet and adding 50% of friction loss in the fitting. The total equivalent length of piping is 40 plus 20 equals to 60 feet. The friction loss of riser pipes and fittings is calculated next. Using the friction loss of various pipe sizes per 100 feet, convert the friction loss to the equivalent length. In this case, 60 feet or 60 is greater than 100.60 or 60% of values recorded. This is the result. These friction losses are now compared to preliminary main size selection, and the final selection for main and riser is made. The choices are as follows. These are the choices. Using a 21 halves inch main and 11 halves inch meter that has 10.46 psi friction loss, leaving 7.18 psi per riser friction loss. The choice is limited to 11 halves inch and 2 inch riser pipe. B. Using a 2 inches main and 11 halves inches meter that has 11.62 psi friction loss, leaving 6.02 psi for riser friction loss, and riser choices are only the 11 halves inch and 2 inches pipe. The final selection may also depend on whether there is any possibility of adding any length to the riser. The final selection would depend on other variables, in particular whether the main will serve any other building and whether there are chances of further development on the site, perhaps another apartment building. There is no single correct answer. In this case, the solution that seems most economical is 21 halves inch main and 11 halves inch meter with 11 halves inch riser, or 50 millimeter main, 40 millimeter meter, and with 40 millimeter riser. At this point, the information of the upfeed system should be tabulated. The required information includes fixture, units per floor, and the accumulated fixture, the demand flow, and the pipe size. This is the tabulated information for the problem. The first step in this design is to list all the information about the project. The project consists of 20-story public building with 50 psi at community main. The floor 1 to 18 has 3 flush bulb, water closet, 2 urinals, flush bulb, 2 lavatories, and 1 sink. Floor 19 to 20 has 3 flush tank, water closets, 2 urinals, flush tank, 2 lavatories, and 1 service sink. Floor to floor height is 11 feet. Distance from the community main to riser is 40 feet. Second, to determine the main meter and the riser sizes for the system, find the WSFU per floor and the total WSFU the building. For floors 1 to 18, the total WSFU is 846 WSFU for floor 1 to 18. For floor 19 to 20, the total WSFU is 56 WSFU. and the total fixture unit is 902 WSFU. Just add the first and the second result. Third, the next step is to determine the demand load for water in GPM. The system is predominantly flash bulb and the approximate demand load is 902 WSFU equals 201 GPM. 902 WSFU equals to 12.68 liters per second. Number 4, because the bottom floor of the building will be a service for upfeed zones and the upper floors by downfeed zones, a preliminary decision must be made on how many floors each zone will supply and the number of zones required. The upfeed zone is limited to a practical maximum height of approximately 60 feet with a floor-to-floor height of 11 feet. The upfeed system will serve 5 to 6 floors, depending on the depth of the water main. Because on this project, main is shallow, it will be possible to have upfeed zone on the 6 floors if necessary. Downfeed zones also have maximum height. Without using special pressure reducing and control valves, in this design, the flush tank water closets on the top floor requires a water pressure of 15 psi to operate. So if 15 psi is required and the water pressure increases 0.43 per psi per foot, then 15 psi times 0.0434 psi equals to 34.6 of vertical distance would require between the tank and the top fixture to provide the pressure required. The zoning of the downfeed system is determined next. Because the water pressure is increasing as it goes down the downfeed riser, the vertical distance that a zone can service is limited to the maximum amount of pressure that can be put on the lowest fixture, and still have to operate properly. This maximum pressure varies in the type and manufacturer of fixture being used. The allowable pressure may range from about 45 to 60 psi. In this design, the pressure of 55 psi will be assumed to be preferred maximum. Thus, the downfeed zone can be 55 psi divided by 0.434 psi per foot or about 126 feet because there will be some more pressure loss from the friction in the riser pipe. The zone may be slightly longer computed. In review, then the upfeed portion of the system can easily service bottom 5 floors. This leaves 15 floors to be serviced by the downfeed system. With a floor-to-floor height of 11 feet, this is a vertical distance of about 125 feet, which cannot be served by one downfeed zone. Two downfeed zones will easily provide the water service required to 15 floor that upfeed zone. Note, in reviewing the schematic downfeed water supply system, that the house tank used to provide water from zone 2 must be placed high enough above the fixture. It is to supply that there will be sufficient pressure for the fixture to operate efficiently. In this case, 20 psi will be required to operate the flash bulb water closet, calling for the height of 20 psi times 0.434 psi per feet, 46 feet, plus a short distance to overcome friction, the riser. In metric units, for the design, 380 kilopascal will be assumed to be the preferred maximum. This means that the downfeed system can be 380 kilopascal divided by 9.8 kilopascal per meter or about 38.8 meter. As there will be some pressure loss from the friction, the riser, the zone may be slightly longer if required. Number 7. The accumulated information for the upfit zone is now tabulated, with each floor listed along with the fixture. The accumulated fixture unit must service above, so the fixture units accumulated total of what must be serviced. The demand flow GPM for the accumulated fixture units and the pipe size selected. 8. Static head loss is determined. The vertical height of the riser from the top of the main to the top of the upfeed zone is about 55 feet. Static head loss change in pressure static equals to 0.04. 55 feet equals to 23.87 psi. Pressure required to operate fixture at the top fifth floor is upfeed zone. Flush valve, water class to 20 psi. Pressure left to overcome friction. This is the given. In metric units, the vertical height of the riser from the top of the main to the top of the upfeed zone is about 16.8 meters. Static head loss change in pressure static 9.8 kilopascal times 16.8 meters equals 138 kilopascal. Pressure loss remaining to overcome the friction. 380 minus the quantity 165 plus 138 equals to 380 minus 303 equals to 77 kilopascal. At this point, the service main should be selected for 902 accumulated water supply fixture unit with a demand loads of 201 GPM. This is the result again. Because the main distance is given as 40 feet, the friction loss for each pipe would be, this is the friction loss computation. The friction loss in meter is checked next. Before the riser selection can be made, the water supply fixture demand loads in the feed zone must be calculated and put in the tabulated form. Available pressure left to overcome the friction and the converted. This is the computation again. Riser pipe selection as follows. This is the selected riser pipe. The size of the riser may be decreased in the upper floor as GPM decreases, as long as the friction loss for each segment does not increase. While the 2-inch riser could be used, the 21 halves inch pipe is selected to allow some extra pressure at the top fixture. Now complete the tabulation for the upfeed zone. In metric units, while the 50 mm riser could be used, the 65 mm pipe is selected to allow some extra pressure at the top fixture. Once all of this information is tabulated, the design is complete. Pumps. A pump is a mechanical device used to move fluid by converting mechanical energy to pressure energy called head. In buildings, pumps are used to circulate or pump water in domestic hot and cold water system, hydronic, and chilled water distribution system. Feed water systems for boilers and chillers, condensate returns system, well systems, waste system, treatment system, sump installation, and other process piping system. There are two types of pump. The first one is positive displacement pump. It is a pump with expandable cavity on the suction side of the pump and a decreasing cavity on the discharge side. Example is the human heart. Another is centrifugal pump, which is made up of an outer casing that has a rotating wheel-like component called an impeller, with a stationary cavity created by the casing and called the valve. Pump drives. Pumps are driven by a drive. It is usually created and consists of electric motor and a fuel-generated engine. A fuel-generated engine is temporarily used for emergency application. Pumping configuration. In heavy loaded building, installing several pumps either in series or parallel is necessary. Using this strategy, the pressure can be increased and water can be scattered all throughout the building. There are two types of pumping configuration. The first one is parallel. In parallel, two pumps having different flow rate can be installed. The small pump can be configured during low to average demand, while the large one can be used on high demand periods. And it will also help during its maintenance because the pump that is not needed repair can be used while repairing or maintaining the other. Another one is pumping series. In series, two pumps were joined in one line piping system. It doubled the head at the same flow condition. It contains higher suction than the parallel pump and very cost effective for high discharge head. Pump performance. The fundamental performance consideration of centrifugal pumps are capacity, total dynamic head, brake horsepower, pump efficiency, and pump speed. These characteristics and related terms are discussed in the following section. First is pump capacity. As you notice, pump capacity commonly measured in either gallons per minute or GPM or liters per minute or cubic meters per hour. Pump capacity depends on pressure, temperature, and viscosity and the specific gravity of the liquid being pumped, on the size and the speed of the impeller, and the size and shape of the cavities between the impellers. Total dynamic head. It is a pressure difference expressed in feet that represents the measurement of the height of a liquid column that the pump can generate from kinetic energy imparted to the liquid. An illustration to clarify this unit of measure would be a pump shooting a stream water straight up into the air. The maximum height attained by the water stream would be the total dynamic head produced by the pump. To pump water at specific flow rate, the total dynamic head generated by the pump must overcome the head of the system through which the pump is pushing water. Thus, total dynamic head developed by a pump must overcome a combination of static head and friction head in the piping system. As you can see, the total dynamic head is change in PTDH equals change in pressure static plus change in pressure friction. Head is a term that have units of length and pressure PSI, PA. The principal reason for using head in units of height instead units of pressure to express centrifugal pumping capacity is that the pressure from the pump will change if the specific gravity of the liquid changes, but the head will not change because most centrifugal pump can move various fluids with different specific gravities. It is simpler to express the pump head in feet. In system with water, this change of specific gravity is generally not a consideration because most pump performance criteria is based on a specific weight of water. Power and hydraulic efficiency. The work performed by a pump is related to the total dynamic head and the weight of the liquid pump on a specific time period. Brake horsepower or BHP is the actual horsepower delivered to the pump shaft under stated operating condition of the pump, where horsepower is 550 foot per pounds per second. Pump output is the water horsepower or WHP delivered by the pump. The water efficiency and water of a pump, sometimes called the hydraulic efficiency, is expressed as percentage of hydraulic horsepower to BHP over the recommended operating range of indicated impeller size or sizes. It describes the change of centrifugal force expressed as the velocity of the fluid into pressure energy. The relationship between BHP, WHP, and N water of a pump is brake horsepower equals to water horsepower over water efficiency. Water efficiency of a specific pump or impeller configuration will vary with flow rate and head, but some configurations are better than the other at a specific flow rate and head. A pump operating at high efficiency uses less energy other than with low efficiency. The best efficiency point or BEP is the operation at which pump must most efficiently convert shaft power to flow because there will be no radial deflection. On the other hand, operation outside BEP results to unstable conditions like vibration, cavitation, and erosion. BHP, the power delivered to the pump shaft under stated operating condition of the pump is found by the following expression. BHP, the quantity Q times change in PTDH times SG over 3960 times efficiency water. Net positive suction head. Pumps are designed to pump only liquid, not vapors. Vaporization of liquid being pumped should not occur at any condition of operation. As discussed earlier, vaporization results in cavitation, which is undesirable because it can obstruct the pump, impair performance and flow capacity, and damage the impeller and other pump components. To prevent cavitation, a pump always needs to have sufficient amount of suction head present to prevent this vaporization at lowest pressure point in the pump. Net positive suction head (NPSH) is the term used in inlet of a pump sucks liquid into pump, which expressed in height, feet or meter. The minimum head required to prevent cavitation with a specific liquid at a specific flow rate is called net positive suction head (NPSHR). NPSHR is gathered through tests varying with the speed and capacity of the pump. NPSHA is directly related to system design, while NPSHR is directly related to pump design. Technically, NPSHA must be greater than the pump NPSHR in order to pump operate properly. Because of it, on the contrary, suction pressure is too great and the water being pumped will spontaneously vaporize in the pump casing, causing cavitation. Pump affinity laws. Pump affinity laws are scientific relationships that describe changes in pump capacity, total dynamic head, and BHP when a change is made to the pump speed, impeller diameter, or both. The affinity laws are only valid under condition of constant efficiency according to affinity laws. Capacity changes in direct proportion to impeller diameter ratio, where the subscript 1 refers to the original impeller diameter and subscript 2 refers to the new diameter. Capacity 2. Capacity changes in direct proportion to the ratio of the pump impeller speed, where speed is in RPM. The subscript 1 refers to the original speed and subscript 2 refers to the new speed. From this relation, it can be observed that the capacity of the pump can be increased by increasing pump impeller diameter or pump speed. Manufacturers make several impeller sizes that fit in one size of the pump casing, making it easier to change to another impeller size. variable speed drives, such as motors. Control flow by changing pump speed. Total dynamic head changes in direct proportions to the square of the impeller diameter ratio, where subscript 1 refers to the original impeller diameter and subscript 2 refers to the new diameter. Total dynamic head changes in direct proportion to the square of the ratio of the pump impeller speed, where subscript 1 refers to the original speed and subscript 2 refers to the new speed. Increasing impeller diameter speed will increase the pump total dynamic head. Because of the square function of the expression, even slight changes in the impeller size or speed produce large changes in total dynamic head. Brake horsepower changes indirectly proportional to the cube impeller diameter ratio, D2 over D1, where the subscript 1 refers to the original impeller diameter and subscript 2 refers to the new diameter. Brake horsepower 2 equals to brake horsepower 1, where D2 is greater than D1. Because of the cubic function of the expression, increasing impeller diameter speed will significantly increase the bhp required to drive the pump. Slight changes in impeller size or speed result in a need for larger drive size and power consumed. Capacity Q, total dynamic head, and bhp can be found by this equation if changes are made to both impeller diameter and pump speed, where the subscript 1 refers to the original impeller diameter and speed, and subscript 2 refers to the new diameter and speed. Pump performance curves. A pump performance curve is a graph that shows the flow rate that a specific pump model and impeller size is capable of pumping over a range of pressure differences. The pump curve also shows pump speed in rotation per minute and other information such as pump size and type and impeller size. The pump performance curve is produced by a pump manufacturer from actual test performance single model of pump. Manufacturers usually incorporate several performance curves on a single chart, with each curve representing a different impeller. Here are the example. It is a pump performance curve for a specific pump model having several impeller sizes. Using pump performance curves, two variables affect pump performance: drive horsepower and impeller size, total dynamic head, and pump capacity. These hydraulic design conditions are specific to a particular piping installation and are used to determine the required size of pump. The first step in selecting pump size is computing the system head, the sum of the static head and friction head of the piping system, and establishing the required flow rate of the system. The pump overcomes system head by producing total dynamic head, so system head relates to the total dynamic head. The required system flow rate is tied to the desired pump capacity. The intersecting point of the pump performance curve where the desired pump capacity and total dynamic head match the installation's requirement is known as the operating point. The operating point will always fall on the pump performance curve on a specific impeller. Selection of the pump impeller size and drive horsepower are based on the operating point. In most cases, when selecting a pump impeller size, desired pump capacity and total dynamic head needed to do not intersect a performance curve exactly. That is, the intersecting point falls between two impellers. In this case, the larger impeller is selected. However, this moves an operating point to the performance curve of the selected impeller. Movement is up and to the right because the system head increases with an increase in flow rate. To control the flow rate of the centrifugal pump, it is normally necessary to further restrict flow friction head in the system is increased and the flow discharge piping is reduced to the desired flow rate. When selecting a centrifugal pump and impeller size, the pump efficiency under hydraulic design condition, example, capacity required and total dynamic head, must be taken into consideration. Theoretically, the BEP of the ideal spot of the pump to operate. So when evaluating several different pumps or impeller diameters for a specific pump model, the pump that best matches the design condition, capacity, and head, and comes closest to BEP is hypothetically the best choice. Practically, selecting the pump with the flow and head requirements are slightly to the left of BEP makes good engineering sense. This offers the capability to make adjustment if necessary to flow and head conditions for the system to operate properly while providing a high level of efficient operation. For optical performance, it is desirable that pumps operate within a range of 70 to 115% BEP. With small pumps, manufacturers typically match a drive to the pump. For a large pump, the designer must select the driver based on BHP related to the selected pump model and impeller diameter. Selecting the drive large enough to handle the largest impeller that can fit in the pump casing can eliminate the need for drive replacement if the pump. Water softening. Hard water. The presence of excess calcium or magnesium mineral ions water results the water being referred to as hard water. Calcium and magnesium mineral generally are measured in grains of hardness per gallons of water per parts per million and milligrams per liter. Soft water has a hardness of 3.5 GPG or less. Hard water has a hardness of 7 GPG or more. Softened water is any water that is treated to reduce hardness. Water hardness can be tested by independent water testing laboratories or some governmental health departments. Most public community water systems record the hardness of water they supply. Mineral ions in hard water react with mineral, metal component, and chemical agents, which causes two main problems in plumbing system: scale and hard, crusty deposit visible on taps, shower fittings, toilets, and water-using appliances, such as boilers, water heaters, which clogs pipes, fixture and appliances, reducing equipment efficiency and increasing energy costs, and scum. This reduces the cleaning effectiveness of detergent used for. Water softeners. Water softening is a process that reduces and removes calcium and magnesium ion from hard water. There are many processes used to soften water. The most used softening method in residential installation are ion exchange and reverse osmosis. They are introduced in the section that follow. The industrial methods used are very complex and include electrodialysis reversal, EDR, flashpoint distillation, thin film evaporation, and lime soda ash softening. Ion exchange water softener. An ion exchange water softener operates by passing hard water through porous resin beads that have soft sodium and potassium ions attached to them. The ions contributing to hardness are replaced or exchanged with other ions that do not contribute to hardness, thereby softening the water. After softening a large quantity of hard water, the beads become saturated with calcium and magnesium ion. The resin beads then need to be regenerated by flushing a brine solution through the beads. The sodium ion in the brines recharge the beads so they will again be able to exchange the hard ions for the soft ion. Frequency of regeneration depends on the hardness of the water, the amount of water used, the size of the softener, and the capacity of resin to remove hardness. It is done manually, automatically with a timer, or founded by the demand-initiated control based on quantity of water used. The ion exchange softening process adds sodium to the water, which could be troublesome for individuals on sodium restricted diet. Reverse osmosis water softener. A reverse osmosis water softener works by forcing water under pressure against a semi-permeable membrane, where water molecules form a barrier that allows other water molecules to pass through while excluding most suspended and dissolved material, including ions contributing to hardness. It is called reverse osmosis because mechanically pressure is used to force water flow in a direction that is reverse of natural osmosis. Example, from a dilute to a concentrated solution. These softeners typically incorporate an activated carbon filter which can provide added treatment for volatile organic compounds or VOCs, not treated by membrane itself. As a result, they are often called water-treated treatment devices. In residential application, maintenance of reverse osmosis softener involves the replacement of a membrane cartridge every 2 to 3 years and replacement of the carbon filter cartridges once and twice per year. Here is an example of load analysis worksheet for domestic water computation.
If you have any questions, please comment it down below. Thank you for watching.